Hello everyone, and welcome to another of my video lectures. This is actually going to be a supplemental for how to do some of the activities that you're going to be required to do using Keysight's advanced design system. So I'm going to go ahead and start this off by opening up my my advanced design system distribution. And so when you first open up Keysight Advanced Design System, you're going to be greeted with a window very similar to what you see here. I'm going to walk you through the process of creating a new workspace, but you could alternately just use one of the previous workspaces that you've built other models in before. So creating a new workspace, I'm going to go hit Next. I'm going to name it something, so my workspace work is more than sufficient. You can name it anything you want to, like Lab 1, Lab 2, or any host of other things, or EE339. So next, okay, so this you can always, with the libraries, you can just leave them as the defaults for anything in this class. If you start doing much more development work, you might find that you have specialized site libraries that your employer might produce. This is here where you'd select that, or if there's certain items that your group as a whole tends to use, then they'll tell you if you need something special. But for everything that we're going to be doing, this analog RF library is more than sufficient to handle it, and that's the default for Keysight's ADS. So again, here, this you can call anything you want to, but this library name allows you to select components later on and place them into other schematics. You're not going to really be doing it with that during this class. Alright, so here, this is personal preference on what you want to select. I tend to put it in millimeters, mostly because a lot of the mathematics is easier to do in the SI units or metric, so I tend to leave it in millimeters. However, there are a lot of data sheets out there that put the component values in, or the component layout dimensions in mils and other things. So again, it's really a personal preference. If you find yourself using a lot of data sheets that are written up in mils instead of millimeters, or you end up doing a lot of stuff where you're dealing with mils specifically, then it might be easier just to leave it with your mil layout standard ADS. But for the purposes of this discussion, I'm going to go ahead and leave it in millimeters and move forward. Alright, so now that I've gotten this, it's telling me kind of a summary of what I've selected, and I'm going to go ahead and hit Finish. Alright, so from here, this is the folder view, and under this folder view will be anything that you create and put into the workspace. Excuse me. So what I'm going to do for this is I'm going to just open up a new schematic to get it going. But you could also create a new layout directly, or create a symbol view, or a new data display window, and you can do a lot of other things here. There's a lot of stuff up here that you can deal with, but for right now we're just going to hit a new schematic and move forward from there. So I'm going to call this antenna. My reason for this is that our first lab we're actually going to be simulating an antenna, so it's going to be something similar to this, and I'm going to talk a little bit about how building one of these inside of the environment. So we'll just go ahead and call it an antenna. I'm going to enable the schematic wizard. You can, if you know what you're doing and you want to just put them all together without it, you can just go ahead and disable it and go finish, and then you can just kind of start building your model. But for the purposes of this discussion, again, I'm going to go through the schematic wizard. So when you set it up here, you can choose whether you want to just do a circuit or you want to do a simulation. If you set up a simulation, then it walks you through putting the S-parameter simulator controller in the blocks. So this might be helpful if you don't want to go navigating through the palettes. So I'm going to say Next. I'm going to create a 2-port network, but you can create any kind of amount. This N port allows you to create as many ports as you want to. You just have to select it up. You can also select amongst different kinds of systems that have basically templates that are available to them, like a mixer development or DSP component tests or oscillators or whatever. But for our purpose, I'm just going to go 2-port simulator and go Next. Instead of using the sample design or use existing design, I'm going to say I'll design my own circuit, because in this case we're actually we're going to be taking measurements and then putting that into the environment. Alright, so I'm going to go with linear frequency sweep. That's pretty standard. And you'll notice that it's telling me that it's going to be a S parameter versus linear frequency sweep. So it's going to put in a S parameter simulation controller. It's going to give you a little thing with a display template and 2-port terminations. And then hit Finish. And then it gives you, it's successful, and kind of gives you a couple of things here. I'm going to hit Close. So I'm going to maximize this. So this is what it pops up when you use the schematic wizard and you say you want a simulation as well. I'm going to go ahead and delete this, and then for the purposes of our discussion, I'm going to delete this second terminator. The reason why is because we're only going to be using a 1-port device. You notice how I just kind of was able to rotate that? If you hit Control R, that allows you to rotate components or anything that you have selected. So that's helpful. Another one that can be useful is if you do Shift X. Then what it does is it mirrors it over the X axes, wherever you point at. So you'll notice now that before minus was going down towards the ground, but now plus is down, and they're both connected to each other. The reason why that happened is because in ADS, whenever you overlay a port connection on a component, which is this little blue square, over another one, then it creates a connection whether or not you intentionally put it there. So what happened is when I flipped it, both ports got connected because the negative side was already connected, and then I flipped it in the positive side. So you can just select this and hit delete, and then I'm just going to rotate this again and just put it back up. But you could also just do you could mirror it again, and you would get it back to normal, and then you'd still have to delete that line. But just you can also do Shift Y and mirror it about the Y-axis. That's not going to be that interesting, but I'll go ahead and do it for you. So see how it kind of changed where the plus is on this component, whether it's on the left side of the item or the right side. Sometimes this is helpful more specifically for just kind of getting everything laid out the way you want it to get organized in a way for the schematic. And so it can be helpful, and so I just figured maybe you might want to know that. So another thing is that when it puts down the simulation controller, or the S parameter controller, it just sets it up with the defaults, which is 1 gigahertz to 10 gigahertz and 100 megahertz increments. We don't want to do it for this simulation. I'm going to do it to 800 megahertz to 2 gig. Primarily that's because the systems we're going to be using to measure the antenna are only going to go up to a maximum of 3 gigahertz, and the operating band of the antenna is lower than 2 gigahertz. So it's actually about 1 gigahertz. So I just want to have a range over which you can see the entire response of what the antenna is going to look like. Now I'm going to change the step here as well. I'm going to set it to 1 megahertz. You can put it to 10. You could probably, in this case, I probably could leave it at 100. But either way, this is just the resolution or the total number of points that you're going to have in your sweep. So the technology that we're going to be simulating and doing a lot of, and we did some of this stuff last semester, is T-lines microstrip. So that's transmission lines microstrip. Now for any kind of transmission line, whether it's microstrip, strip line, coplanar waveguide, or any other component, you need to have a substrate definition. So this block right up here is the substrate definition block, and I'm going to hit escape, and it kind of goes back to, notice how there's nothing highlighted or moving around with my cursor. With the substrate definition, you can go in here and manually change all of these values. Now you could change them from the schematic window, but then you'd have to know what each one of these are. So one thing to point out is that if you double click on MSub, then when I select a parameter, say this H, which is 0.25 millimeters, it tells me what that actually is. So in the case of H is the substrate thickness. So with the FR4 fiber board that these antennas are built on, your microstrip lines are made of, and everything else, it's between 1.52 and 1.6 millimeters, so I'm going to stick it at 1.6 millimeters. My epsilon R value, which is your dielectric relative permeativity, that is going to be a 4.2. So, and this thing calls it dielectric constant, or relative dielectric constant, which it's the same thing. MUR is the relative permeability. I just leave that alone. Conductivity is the conductor conductivity in Siemens per meter. So I usually switch this up to 4.0 e to the 8. The reason why is because that's a pretty common conductivity value for copper. There's other ones that are available as well, like depending on which data sheet you look at. So just to make it realistic, you want to modify this parameter, because 1 e to the 50 means it's nearly perfect. It's outside of the scope of what the computer is going to be able to calculate, so it's effectively going to be a perfect conductor. Now the reason why it's automatically set at 1 e to the 50 is because this other parameter that's down here, which is the conductor thickness, notice how it's set to 0. Since a conductor can't conduct if there's no conductor to conduct on, having a 0 thickness makes it impossible to for, say, since I changed this conductivity value, this 0 conductor thickness is going to be unreal, non-realistic, and it's not going to simulate very well. So I'm going to change this to the conductor thickness on the FR4 substrate that I have, which is 0.034. And again, this did cause some confusion last semester, because T sounds like thickness, and people thought it was like the thickness of the board. But again, this is the thickness of the conductor, or the copper edge. Tan D is the dielectric loss tangent. For FR4, it's actually kind of high at 0.036. That's pretty much an average value. Again, you can find lots of different kinds of values around, and it does vary based on manufacturer, and it kind of moves around. So, pick one, use it for your simulations, and then you can compare it to reality, and then you can get kind of an idea about what your board actually is. And one thing you could do is, if you have the ability to test dielectric constant, you could actually just create structures on the board material you're going to use, measure them, and then determine what the loss tangent is and what the dielectric constants are. And then that'll make this model much more accurate. But again, that's just kind of digressing. We're not going to go through that in this semester. Rough is a conductor's surface roughness protrusion height. So I'm going to leave this alone. I'm going to say that it's perfectly flat. But if you wanted to simulate a structure in which you were interested in how rough the surface of the metal was, especially at higher frequencies, that makes a big difference. But in this case, at these low frequencies, around 1 gigahertz, it's not that critical. But again, it does. If you knew what that was, it would help with your simulation. So cond 1 is the first conducting layer, and this is for the layout option. So layers on which the microstrip metallization will be drawn is cond, which is conductive layer 1. A layer on which the air bridges will be shown or will be drawn is, that's just leave these alone. You don't have to adjust with them. Dielectric 1 is for layout option, layer on which the dielectric capacitance areas will be drawn, so on and so forth. This is all for our layout, so we can leave that alone for right now. Also, these ones here, you can leave these alone. These are all defaults, but they work for us. And once you're all set up doing the microstrip substrate definitions, you can hit OK. It all populates in here. And so now we can go on to actually building our structure. Now, for the antenna that we are going to measure, it's going to look like basically two lines. One's going to be a feed. And so what I'm going to do is, instead of calling this TL1, I'm going to call this feed. Right? And then the other one I'm going to do is I'm going to put up a second transmission line, and actually because I'm kind of getting out of it's starting to overlay a little bit, I'm going to put a second substrate or a microstrip line, and instead of calling it TL1 again, I'm going to call this the patch. Right? So this is a very simple antenna, but again, I'm going to kind of go through this a little bit. For my width of my feed, I'm not going to go through right now, but what you could do is you could go up into your tools and go to your line calc and start line calc, and then calculate what a 50 ohm transmission line is for this particular substrate material. What I could do, I'll go ahead and do this. So 4.2, height is going to be 1.6, and that's millimeters, not mils. Thickness, I'm going to leave that alone. 40 to the 7, I'll just leave that alone for right now. It's not important. I'm going to put this at 1 gigahertz, which is the operating range of this antenna. And then I'm going to switch this to 50 and this to 90. And I'm going to synthesize. Oh, wait, I want to change it to the units that I'm interested in measuring. So synthesize. So it's about 3.16 millimeters for a 50 ohm transmission line, and about 41 millimeters for a 90 degree or a quarter wavelength. So what I'm going to do is I'm going to take these values, and let's rearrange our desktop here a little bit. This way I can see it. I'm going to put up a variable block, which is right here. So with the variable block, I'm going to double click on it, and I get my parameters. So my first parameter is going to be WZ0, which is, for a 50 ohm transmission line, what is the width? And I'm going to set the value to the value that I came up to in line calc, which is 3.16. And then I'm going to do add. And now what I'm going to do is I'm going to take this one, and I'm going to change this to L90, which is the length of a 90 degree impedance transformer, or a 90 degree transmission line. I'm going to change this to 41.8. And I'm going to hit apply. Alright, so now I have L90 and WZ0. And actually, I'm going to go back in here, and I'm also going to do L patch. Which is going to be 2 times L90. Oops. And see how I hit OK instead of add? That caused my problem. So again, I'm going to re-put this 41.8 and then do add. And then I'm also going to do width of patch. So it's going to be W patch. And this one I'm going to also do as 2 times L90. And the reason why I'm picking 2 times L90 is I'm not going to give you the numbers that you're going to calculate or you're going to measure on the board on Thursday. What I'm actually just going to do is just show you what a half wavelength square patch is going to look like. But you would put in L patch and W patch, you would put in exactly what you got for your measurements when you take your lab. So now with these values all set up, I'm going to say, okay, what's my width of my patch is going to be W patch, and my length is going to be L patch. My width of my feed is going to be WZ0, and my length is going to be L90. Alright, so one thing you should be very conscientious about when dealing with ADS is that inside the variable block, if you use these, notice how I don't have any units inside of the variable block, but I have units here. If you put units in the variable block, then, so suppose I put 41.8 millimeters here in L90, then when I put L90 in here, it would be 490, or 41.8 millimeters, which would make it much, much smaller. Right, so what you have to do is pay attention to these units. Only use the units once on the schematic to define a particular parameter. If you don't do that, you'll run into some problems, and many of you did last semester. So now what I'm going to do is I'm going to use this wiring tool and connect up my components. Alright, so now that I have my substrate definition, I have my S parameter controller, I have my variable block set up, I have all of my model put together, I'm going to go ahead and hit the simulate block. Now, this is a data display window. When you pop this up, for this particular purpose, I'm going to just put in a rectangular plot, which is that square right there. And I'm just going to select S11 because that's all I have available, and DB, and hit OK. Alright, so this one's showing me 2 points. And what I'm going to do here is I'm going to put in two minimum markers. I guess I can't do 2. I'll do a second marker. The reason why is because it's doing minimum of the entire trace, which is the lowest point. So if you look here, what it's telling me right now is that it's radiating pretty good. I'm getting a pretty good return loss at 887 meg. I'm getting a pretty good return loss as well at 1.783. Now, one thing to point out is that, if you multiply this by 2, you're going to get that. That's because what you're looking at is you're looking at a harmonic. So the structure is a half wavelength here, and it's a quarter wavelength here. So the item still operates relatively well over those 2 different ranges, and that's why you're getting those 2 different nulls. Now, remember this when I go and do the layout. Okay, so the next thing I'm going to do is I'm going to show you what happens when I use a different component for the second piece. So instead of using this MLIN here, what I'm going to do is I'm going to use an ML open circuit. So I'm going to rotate this around, and I'm going to call this again. I'm going to change this to W patch, and I'm going to change this to L patch. Delete this, move this over, connect it, and then I'm going to simulate. And actually, before I simulate, I'm going to do this. I'm going to hit right-click, go to History, and turn it on. So the history is going to show me what the difference is between the 2. Now, so I didn't change the parameters, but I changed the component model. See how that component did basically the same thing as the previous component? You can actually see that it's essentially the same exact model. Now, the reason why I did that is just to point out that sometimes you want to be able to use a component that doesn't have additional ports or additional points for which it can connect to. In this case, with this version of ADS, doing this or doing this made no difference because ADS is smart enough to know that this, without an extra connection to it, is effectively the same thing as this open circuit connection point. Some versions of ADS previous, this is the 2016 version. If you ran the 2015 or the 2013 version, this would actually cause a substantial difference here. So I'm actually just bringing this up to kind of point to you that you may want to attempt to try to use the correct component for the correct kind of model. Only use a 2-port component like this if you're making 2 connections to the device in the measurement system. So in the case of this antenna, we're only doing 1 port, so I really only want to use these 2. So this is the correct way to do it. So because of that, I'm going to go ahead and do this and move this over to patch and leave that alone. So now that I have this original simulation, and I'm actually going to go ahead and turn the history off on this, I have my simulation here. I'm going to go ahead and switch it over to my schematic. So this is something that you may not have done from previous labs, but you go into this layout tab and go to generate update layout. Once I do this, I'm just going to hit OK. It's going to populate a layout component. So this right here is my layout component, and if I double click on it, it's effectively this L patch and W patch, and since they're both 2 times L90, it's this square. And then you have your feed point. Now notice how there's nothing really connected, but there's a point here to connect to. So in order for you to do an EM simulation, you actually have to use a port designator. So in this case, I put P1 right there on the input of the feed point. By doing that, I can now actually go up here and do a simulation setup. So under, again, I did that kind of quickly. So you go to EM and then simulation setup. Right? Once you're here, you can select what kind of setup you're going to do. You can either do a standard EM simulation or you can do an EM co-simulation. We're going to do a standard EM simulation. Now, ADS is pretty smart and will tell you when there's an error, where there's something that's not defined properly or not set up correctly. So in this case, I have these markers saying that there's warning. So it says substrate is not found, so I have no substrate defined. There are no layout pins on the layers mapped to the substrate. So again, this is the same kind of thing with no substrate value. So what I'm going to do is I'm going to go ahead and take this substrate and create a new one. And we're going to call this FR4. And as a template, I'm going to I'll just use the 25 mil Illumina. Okay, so here we go. So the reason why I use the 25 mil Illumina is so that I have an automatic ground plane cover. So this creates this structure inside of the ADS substrate model, so that all I have to do is now modify the components. So notice how I click on the space that's like the air gap between these 2 layers. This is the top layer and this is the bottom layer. It allows me to change this material. Right now, all I have as choices are air and Illumina. So I'm going to actually modify this because I need to have a new one. So I'm going to do an add a dielectric. And so for this dielectric, I'm going to call it FR4. And now I'm going to input the values that I put in my original model. So tan D 0.036. And that's good enough for this particular piece. So I'm going to hit OK. And so now what I'm going to do is I'm going to select FR4 from this board, and now it's FR4 and it's telling me it's 25 mils thick. Well, I want to change that to 1.6 and set it up right here with my millimeters. So now I have a 1.6 millimeter FR4 board where the conducting layer 1, or COND1, is set up as the conducting layer on the top surface. Now I know it's set up to a perfect conductor. Again, all I have is Illumina and FR4. So I'm going to go ahead and create a new conductivity. So add a conductor, and I'm going to go ahead and modify this and call it copper. And I'm just going to leave it at 4.1 e to the 7. I could switch it up to the e to the 8 that I did before. And actually I think I'll go ahead and do that just for consistency. Hit OK. And now what I'm going to do is I'm going to say this is copper. And as soon as I do that, I need to change this thickness. So 0.034, which is what I put in from my original substrate model. And I'm going to put this into millimeters. So there you go. That's all set up. I now have a conducting layer, air. I have my substrate layer, and I have my bottom cover. I'm just going to make this a perfect conductor for the sake of this simulation. Later on, I'll kind of go into detail about why we would modify this and how we would go about building a lower board so that we can simulate a much more realistic-like structure. But for this point, I'm just going to show you how to go about doing this for the lab. So once that's all set up, you hit X and you hit yes, so you saved it. That's what my substrate is. Notice how my warnings went away. I only have one port, which is P1, and it goes to ground. My frequency plan, I now have to set this up, so I want to go to the same values that I did before, 0.8 to 2 gigahertz. I'm just going to leave it with 50 points. This is actually an adaptive sweep. So what it does is it kind of finds the correct points and then maps a kind of an interpolation between data points to give you a fast model. So there's a big difference between what this simulation is going to do and what your previous schematic simulation did. Your previous schematic simulation did it based off of theory of transmission lines. This one's going to do it based off of all radiative energy coming off the board using what's called a method of moments, or a MOM simulator. That's why it says MOM microwave. Now, if you might have a FEM capability, like I do in this case, and FEM will also do it, but we're going to go ahead and kick it over to Momentum because that's actually the faster one. FEM does what's called a finite element method, and it's a much longer process, and it gives you a different kind of a model and allows you to actually model 3D structures as well. But since ours is planar and mostly 2D, we're going to go ahead and stick with the Momentum microwave. So now that this is all set up, I can go up here and click EM, Simulate, where you see there. This is also Stop Simulation, but I'm going to go ahead and simulate it. Now this will take a little while to do, but because my computer is pretty fast, it goes by relatively quickly. So, notice how this looks a little bit different than what my previous one looked like. And so what I'm going to do is I'm going to go ahead and use the Data tool, Tools Data File tool. And I'm going to go ahead and create a data list with a touchstone file. So write data file from dataset. And I think it's MOM-A that I have to use. We'll find out in a second. I'm going to set this to real and imaginary and keep it in Hertz. S, touchstone file, output file name. And I'm just going to browse to, right now it's in the Workspace. I'm going to put it to my desktop so that I can see it later. And what I'm going to call this is EM Sim. Save. Alright, and then as soon as I hit write to file, okay, apparently I have to save it as S1P instead of doing it as a star. So whatever, I'll go ahead and do that. So write data to file, and the write was successful. Now what I'm going to do is I'm going to go back to my this simulation, which is my schematic simulation, and I'm going to copy this over. And I'm going to add a data file object, which is something we did last semester. So in this case, I'm going to do a one-port S1P component. Double-click on this, browse, and again, I'm going to go to GUI and desktop, and now I should be able to do EM Sim S1P. Open. Okay. So now that I connect this up, what we're going to see what the difference is between these two different files. Here we go, back to antenna. And see I have S11 on here. I'm also going to add S22. Notice how effectively I shifted over by some amount to the left, actually, from the item. This is pretty common, and this happens a lot between our, when we're doing radiative structures, between our standard circuit simulators and our electromagnetic simulators. So I'm going to go ahead and put up a secondary marker here. So again, the same kind of thing. I'm going to do a minimum marker, and I'm going to put another marker down here. And you can notice too that I'm also getting another little structure over here, which could be some other kind of multiplication or addition of some additional items. And so notice how this is actually giving me a much sharper null, but it's shifted to the left. So if this was really critical for the frequency that I was selecting here, this would be a problem, and I'd have to tune this out and kind of adjust for it. Now another thing that's interesting that you can do with layouts, and that's just to show you that there's a difference between the two. Another thing to do is layouts. Now that I have a simulation that's been completed, I can go into the EM and I can go through some post-processing. So I'm going to go to far field. So what this will do is this will actually create a pattern, a far field pattern, and a visualization of what the antenna looks like. So this is the far field pattern on a perfect ground structure. It's similar to what you're going to be simulating yourselves, but one thing to pay attention to is you want to set your simulation setup to something that is within the operating range or near one of those resonant points or nulls that you saw in the return loss plot. By doing that, you can actually get a handle on what the actual gain of these antennas might be, or you can also think of it this way: if the energy is being reflected from the source, then you're not really doing anything with the structure, and so your values aren't going to be quite very nice here. Sometimes it's worthwhile to add some additional frequency components that are particular points or singular points. And that allows you to select a very specific frequency when you go through and do these EM simulations. And I can show you that in just a moment. So on these little tabs here, I'm going to go to far fields. So I was under plot properties, far fields, and you can turn on your antenna parameters. So in this case, this antenna has a gain or a directivity of 6.2, but a gain of -3, which means it's not a very good antenna. It actually loses a lot of energy. It's very lossy, and that's primarily due to losses that are incurred due to current loss. Every time you see stuff like this on the feed, that's not necessarily a good thing. And I'm going to show you something real quick. I'm going to hit this animate button. So this is basically showing you what as the phase is going in, what the current looks like, current distribution on the patch antenna looks like. So you see how it gets really sharp here? There's a fair amount of loss on this transmission line. So if I want to make this better, I might want to shorten the transmission line, or maybe even just change where my feed point is, because I'm probably getting some reflections right here at the input to the patch surface area. Right, and I can go into some of that in detail during the lab if anybody's really interested in how you would want to go through and make this thing a little bit better. But there's a lot of things you can do to make this simulate a little bit better than what you have currently. Alright, so another thing that I'm going to do is, again, I told you I was going to show you how to do individual frequency points. So I'm going to turn off this animate, and I'm going to kick off of this EM simulation. And under your EM simulation setup, what you can do is that you go to frequency plan, you can add, and instead of making this adaptive, make this a single, and then set this to, in this case, we know what our antenna here, we know that it's going to give us a really sharp null at 872 megahertz, right? So I'm going to set one here at 0.872 gigahertz, and I'm going to go ahead and hit simulate again. Okay, now I have this all set up for myself, and I'm going to go back here, and I'm going to go to my EM and do a post-processing far field again. Alright, and I'm going to go to solution setup and go to 8.72, and now you'll notice that there's a lot more current occurring on this patch area, and so that's right where my null point is. If I go to my plot properties in far field, I'm going to go ahead and turn on my antenna parameters, and I still have around a -3 dB gain, which means that my previous frequency point was probably pretty close to this. But sometimes it may not be if you set up your simulation parameters correctly. So this is just one way of kind of identifying exactly what it would be. So this antenna will look like what it would operate at 872 megahertz. You can kind of rotate it around like I'm doing, or kind of adjust it. Now another thing you can also do here is you can create 2D radiation patterns from these 3D patterns, because sometimes they're not that they're not that helpful in identifying certain characteristics. So what you can do is you can go to this next tab over here, which is far field cut, and you can enable it. Now what I can do is I can select this, right now where this green line is, that's where it's going to do the cut. So I can make this at 0 and 90, which is a pretty standard feed cut. I can also do theta cuts, but theta cuts aren't quite as useful because in this particular type of a structure, it's going to give me kind of this donut shape once I select it. So I'm going to switch this over to theta, and I'll kind of, gives you a different radiation pattern. Let's say 70. Okay, that's 80. So we'll go ahead and do that one real quick. So now that I have this thing set up, I can set display cut in data display window. Alright, and so this cut now, you can see that I have two different patterns. So this is cut from the side, but you can see I have a directivity and a gain value. It's not very, my gain is really crummy compared to my directivity. And again, I kind of talked about this in the audio lecture, but directivity is effectively what the antenna would do if it was 100% efficient, meaning that 100% of that energy is converted into RF radiation off of the structure. But in most cases, there's some level of loss. FR4 is pretty lossy material. Also, my structure probably has a fair amount of reflections because the feed point isn't very good. And there's a lot of other reasons why this might happen. But again, this is a side cut. If I go back to my far field cuts, I can actually go here and do my feed cut like I was originally planning. And I'll show you this one. Display cut in my far field, and I'm going to go back to this one. And notice how this one looks basically like what we're seeing there, where you see the dome. So that's how you build 2D patterns in ADS, and that's how you utilize the layout structure. And I gave you a couple of pieces of information about how to use data tools and to utilize the standard circuit simulator. So, I guess, good luck, and I guess I'll see you in class.